Everybody, can you see my screen?
Yes,
Yes,
Dr.
sir.
Ali.
Dr. Ali.
Okay, so you see last class, you were solving the first problem, problem number 2, and I think we were ran out of time and I told you to check at home. Did you all try to solve number 2?
Yes, Dr. Ali.
So question was what is the power rating value?
I got 3.3 megawatts.
3.3.
Megawatt.
Okay. Any other result? Anybody?
Yeah, I got the same result, 3.30 megawatt.
Okay. So everybody the same value?
Yes, Dr. Ali, I also got the same value.
Yeah, it looks like
Yeah, I
okay.
also got the same values.
Okay, yeah, it looks like that is okay. Okay, Manoj, did you get the same number?
I forgot, Dr. Ali. wrote in different papers. So I'm in office right now. So I got it, but I couldn't remember how much I got.
Oh, so the paper is not with you now.
Yeah, it's at home. So.
Oh, okay, I see. Okay, so Samani, you also got everybody. Sindhuja, you also got the same number, right?
Yes, Dr. Ali.
Oh, okay. Okay, so now can you try number 3? This is the not SMS, this is supercapacitor. A supercapacitor is used to maintain the transient stability of a synchronous generator in a power network. The secondary voltage of the transformer of the supercapacitor unit is 1000 volt RMS. If the voltage across the supercapacitor at charging mode is the same as the DC link voltage, then calculate the capacitance value of the capacitor. Assume the power and energy rating of the supercapacitor is 5 megawatt and 10 megajoule respectively, and the firing angle of the VSC converter in rectifier mode is 0 degree. So as you remember, last class, I was telling the structure, the electronic component portion for the SMS and then supercapacitor based energy storage is the same. So at the end, instead of the SMS coil, you need to use a large capacitor. That is the difference. But then the remaining component are the same. Like you need a step down transformer, then VSC, which is voltage source converter, that works both in rectification mode and inversion mode, then DC link capacitor, and then DC to DC chopper circuit, and then finally the supercapacitor. So the structure is the same. So, but then for supercapacitor, the energy storage equation, E equal to half CV square. That is the difference. In case of coil, it is half Li square, and in case of capacitor, it is half CV square. That is the difference. So now, based on that, can you do this one, number 3? Therefore, you look at similar diagram that similar to that SMS, and what is your the question is what should be the capacitor value? That is the question. So the similar structure as to the previous problem number 2 or the very first problem. So as I said, instead of a coil, the capacitor is connected. That is the difference. And even in this problem, in problem 3, there is no chopper circuit. So you don't need to even include the chopper duty cycle. That's why it says voltage across the supercapacitor at charging mode is the same as the DC link voltage. This means that in the circuit, after the voltage source converter, there is a DC link capacitor, and then directly that is connected to the supercapacitor. Therefore, your supercapacitor, which is the large capacitor, that is the actual unit. And for the DC, you can argue that for the DC link, there is a capacitor, but that is not called the supercapacitor. Because in real practice, that capacitor, DC link capacitor, is very small, typically in the microfarad or hardly in the millifarad range, 5 millifarad, 10 millifarad, or around 100 microfarad. That is the range. So that's why that is not called the supercapacitor. That's a simple capacitor. But when the word goes supercapacitor, that means large value of capacitor, at least in the farad range, you can assume that at least 2 farad, 3 farad or more. That is the definition of supercapacitor. So therefore, see the statement. You all know that that energy storage device requires a transformer, step down. So it says the secondary voltage, meaning that for the transformer, primary side is connected to the grid point. In this case, because that supercapacitor is maintaining transient stability of the synchronous generator, so you can assume that the transformer that is mentioned in the second line, primary side is connected to the generator terminal point, and the secondary side, that secondary side has that 1000 volt RMS. Therefore, everybody, this means this is by default the line-to-line voltage, RMS and line-to-line voltage. That is the meaning. And then there is voltage source converter, that unit. Therefore, in charging mode, it says in rectifier mode, the firing angle is 0 degree. So rectifier mode means that is the charging mode for the capacitor. The firing angle alpha value is 0 degree. So therefore, first you need to determine what is the amount of DC voltage being developed with the help of the VSC converter, provided that the alpha value is 0 degree. And once you get that on, then you can relate, because question is find out the capacitance value. So for capacitor energy storage equation have CV square. And then you see the rating are given. Power rating 5 and then energy rating is 10 megajoule. So therefore both ratings are given. So you need to use that 10 megajoule energy rating, that capacity. And then you should be getting the capacitance value. So everybody, could you follow me?
Yes, Dr. Ali.
Yes, sir.
Yeah, so then find out the capacitance value, C value. As I said, you should be getting in terms of farad.
Dr. Ali,
Yes?
I got 10.96 farad.
Yeah, that is the right answer.
I got
Yeah, I
this.
got the same one.
Mhm.
Okay. So Lakshmi,
Yes, Dr. Ali, I also got the same value.
Okay. Venkat? Amani?
Yes, Dr. Ali, I got the same 10.96.
Ah, okay. So, Sindhuja?
I got different, Dr. Ali.
Okay, so what is your VDC value?
450.16.
No, completely wrong. So what equation did you use for VDC? VDC is 3 Vm over phi cosine of alpha.
Oh, okay.
Did you
Okay.
not write that one?
Mm. Yeah, I
Okay.
made
And then Vm, this is the peak value or the magnitude. So the voltage 1000, that will be multiplied by root 2. So
yeah.
Vm will be root 2 multiplied by 1000. So 3 Vm over pi cosine alpha, and alpha is 0 degree.
Yes, Dr.
So then now what is your VDC?
It's 1350.47.
Right, that is right. Yes. Then once you get the VDC, then as I said, energy storage for capacitor E half CV square.
Mm.
Then and then E value is 10 megajoule. This one.
Yes, Dr. Ali. Yeah.
Now using that equation and substituting that VDC value that you got for voltage, you calculate the C value and then let
Okay.
me know. Venkat, did you get the same thing?
Yeah, I'm working on it. Sir.
Okay. Is your VDC value 1350.47?
I need to check once.
Okay.
I got 10.96, Dr. Ali.
Sorry?
I got 10.966.
Oh, okay, okay. 10 point. Okay, then fine. So Venkat, did you write the equation VDC 3 Vm over pi cosine of alpha?
Yes, sir.
And then Vm value is root 2 multiplied by 1000, the secondary voltage, times the root 2. That will be your Vm.
Okay, 3000 by pi.
Yeah, so 3 multiplied, no, not 3000.
Okay, so I mean 3
root 2.
into Vm values.
Yeah, 3 multiplied by root 2 multiplied by 1000.
Okay.
Yeah, yeah, divide by 5. So that's why it's mentioned like RMS. So meaning that you have to convert into peak. So even though it is not mentioned, by default that is the RMS. If it is peak, then it will be clearly mentioned. But even in this case, clearly mentioned that this is RMS. So you must multiply it by root 2. So Venkat, are you working?
Yes, sir.
So what value you got for C?
Uh,
I mean, once you get the VDC value, then use E equal to half CV square.
Is it 3000?
The capacitor value?
No, VDC.
No, 1350.47.
Okay, made a mistake.
So just I said you like 3 times root 2 times 1000 divided by pi, and then cosine 0 1. So
Yes, sir. Now I got this.
what is the voltage value?
1.414. Sorry.
The voltage?
VDC.
Yeah, VDC. Yeah, how much? What is the full number?
I'm getting some different numbers.
Are
Some
you
four,
not
424.
No, are you not using calculator?
No, sir. I don't have a calculator now.
Oh, so what then how
I'm
was
doing in different scientific calculator.
Oh, okay. So maybe some so are you putting the pi value then correctly?
Yeah. The values are there.
So then it should not differ.
Yeah. I'll do it again.
Okay, so it will be 1350.47 VDC.
Yes.
Later you do it, and
Yes.
then you have to use E equal to half CV square, and then put that V value there, and from there you calculate C. So therefore
Yes.
you write down the answer. Answer should be 10.975.
10.97.
Yeah. So
Yes.
10.97. Oh, just a moment. I did not write. Approximately. Yeah. Okay. Hold on. Okay. And then that. I forgot to hear that.
Yeah. Now I got sir. 1350.47, right? VDC.
Oh, yeah. VDC 1350.47. And then you
Made a
calculate.
mistake.
And then the first one was 3.30. 3.3 megawatt. That was the previous answer, approximately. Okay, so therefore move forward. Everybody read number 4. A CSC, this is called current source converter, CSC. This is not VSC, but CSC. Current source based converter based SMS system is used to maintain the transient stability of a 3-phase synchronous generator system supplying power to a grid. The transformer of the storage unit has a turn ratio of 2:1, and the primary side voltage is 2000 volt. Then calculate the inductance value of the storage coil, assuming the power and energy storage rating. Energy rating of the storage coil is 5 megawatt, 10 megajoule respectively. And the firing angle of the rectifier of the SMS unit is 60 degrees. So therefore, whatever it is, current source based converter or voltage source, it can convert AC into DC. The control system is dependent on the current. Accordingly, it is called current source converter. Current is the dominating factor. That's why, but it is the same thing. It will convert from AC into DC in the charging mode or rectification mode. So therefore, it's still the equation that you know, those equations are valid. So can you do, everybody, number 4? So in this case, what should be the inductance value? You have to find out the L value of the coil. So in this case, the L value 0.36 Henry. Okay.
Yeah, Dr. Ali, I got the same 0365 Henry.
Oh, 0.36 Henry, did you get?
Yes, Dr. Ali, I got this number.
Okay. So therefore, everybody, first you need to convert what is the DC value, what is the DC voltage. And because the question is calculating the inductance value, so you have to relate with the energy equation for inductor E equal to half Li square. Therefore, energy capacity is 10 megajoule and L is there, that you have to find out. So you need to know I value, current value. And therefore, you see
So
what?
we need to use half Li square, right? E is equal to half Li.
That equation.
Yes.
But then you have to find out the current. But first you are getting the voltage from that VDC equation. First you are able to get the voltage. And then how to get the current? Because the coil has power rating as well. Everybody look that 5 megawatt. So, and as you know, in case of that coil, power is V multiplied by I. That DC voltage that you are getting, that is the voltage that appears across the coil. So your current is current power over voltage. So therefore 5 megawatt over VDC, that will be your current. And then use relate to that equation, you have Li square. So from there, see that you are getting L value, this one. So is there anybody then who got this one? I mean, Amani first you got, and then Manoj, Kamana, Sindhuja, Lakshmi.
So current is 2500 amps.
Current, how much you said?
2500.
No, completely wrong.
Okay.
What is your VDC, Venkat? Tell me, what is your VDC?
VDC. No, I have to calculate.
Oh, okay. Lakshmi, what is the VDC?
I'm doing it, Dr. Ali.
Oh, okay.
So is it 675.23?
Yeah. Like I myself do like 675.24 approximately, right? So 23, that is it. That is in volt. Yeah. That is right.
Yeah.
And then using that voltage, because that voltage appears across the coil, so using that voltage, find out the current that is flowing through the SMS coil. And once you get the current, then you can relate that energy equation finally, equal to half Li square.
Yeah, the current is 7.404 into 10 to the power 3.
Right, or 7.4, that kilo ampere, right, yes.
A
That
kiloamp.
is right, that is right.
And it is 0.365.
Yeah, the Henry, right? Yeah.
Yes.
Yeah. So like I approximated L equal to 0.36 Henry. Yes.
Dr. Ali, I got 0.3651.
Oh, okay. Okay. So that is okay. So even you can write 0.37 Henry is the even, yeah. I think I just wrote, just truncated 0.36 Henry. But if it is 0.3651, then you can even write 0.37 Henry. That will also fine.
Okay, Dr. Ali.
Okay. Kamana?
Yeah, I got the different result, Dr. Ali. I'm working on it.
Oh, okay. Then go back.
Sir, can you please explain this once?
Sorry.
Can you like?
Oh, okay. So
Tell this earlier.
first, are you not writing that VDC equation? The same equation.
Yeah,
that,
3 Vm by pi. Right?
Yeah. Then in this case, again, that Vm is √2 times your RMS voltage. But the coil is on the secondary side of the transformer, right?
Yeah,
So
yes.
look, the transformer turn ratio 2:1, meaning that 2 is on the grid side and 1 on the coil side.
Yeah.
So the primary voltage is given, which is 2000 volt. Look. So then what is the coil side voltage? So this is the turn ratio, 2:1. 2 is on the grid side and then 1 on the coil side. So the primary voltage is given, which is 2000. Then what should be the secondary voltage? So V1 over V2 is N1 over N2, right? That is the relationship.
Oh, yeah. I got it.
Yeah. So transformer, you have to find out the voltage where the turn number is 1. This means that if the primary side has 200 turns, then secondary has 100 turns. That is the meaning of 2 and 1. So the primary voltage is given. So you have to find out what is the secondary voltage. Because that is always a step down transformer. Just keep in mind, for any energy storage, the transformer will be always a step down. Because grid voltage will be higher, then you have to step down. So that will never ever be a step up, always a step down. Whatever the required voltage is, in this case, the example problem is telling it is half the turn ratio. So then what is your secondary voltage? And once you get that voltage and then that times √2, that will go into your equation, 3 Vm by pi equation. And the firing angle value is at the last line, firing angle of the rectifier of SMS is 60 degree. So your alpha value is 60 degree.
Yeah, now I got the values.
What is the VDC value?
VDC 674.5.
Yeah, okay, yeah. So 675.24, yes. Then from there, using that voltage value, you find out the current for the coil.
Yeah.
So, therefore, power is 5 megawatt, power is voltage multiplied by the current. Then you find I, and then finally you use E equal to half Li square, that equation. Sindhuja, are you getting?
I got different value, Dr. Ali.
For VDC?
Yes.
So what is your VM value? Again, you need to multiply by root 2 times. What is your secondary voltage? The primary voltage is 2000. See the last portion of the third line. See
Yes,
my
sir.
mouse. Primary voltage 2000. But you have to find out secondary voltage. The turn ratio is given 2 and 1. So this means your voltage will be half on the secondary side.
Oh, okay, okay. Yeah.
No, not 2000. So you have to do 1000 because turn ratio 2 is on the primary and secondary side is 1. So voltage will be half.
That's like 675.23.
Right. That is. And use that value in the power equation, P equal to VI.
Yes, Dr.
Your P is 5 megawatt, this one. And
Yeah.
the V, and then find I. And once you get I, then use E equal to half Li square equation.
The current is 7398.04.
Kind of deviated. Maybe you are using some different calculation technique.
Yeah, calculator.
It should be 7404.77 ampere. 7404.
I got 7404.88.
Yeah, oh, okay. That will work. And then use that current value in the E equal to half Li square. Your E is 10 megajoule. Then you see what is your L value. Kamana, did you finally get?
Yes, Dr. Ali.
The same result, 0.36?
Yes, sir.
Okay. So where was the mistake initially?
Yeah, I put cos 30 degree instead of cos 60.
Oh, okay.
That's the mistake.
Oh, okay. I see. Okay. So Sindhuja and Venkat, once you get that result, then you confirm me,
Yes, sir.
and then I will proceed.
I got 0.364 Henry, Dr. Ali.
Okay. So you see, that is fine. I just wrote 0.36.
The current is 7402.
7404.02, that will work.
Yeah.
And then use that one in E equal to half Li square, and then see what is the L value.
Yes. Yeah, 0.364. Sir.
Okay. Okay, then I think everybody is done. Now, I started checking your that class quiz. You remembered that on class 18 there are some class quiz and you submitted the next day. I started looking, and also I started looking your midterm exam too. Then soon, hopefully by tomorrow, you can get the result. I will notify you. So that's why the beforehand I like to discuss the answer so that you can match. Once I will post the grading and I'll write some comment. Okay, so the first one you see, do you remember this one, class quiz? The based on class 18 means at the end of the class 18 there are some questions and you all answered and submitted the next day. I'm talking about that one. For a superconducting fault current limiter, SFCL, after quenching, if the reactor does not return back to its normal operation, then what could be the solution? So what did you write as an answer?
So put the parallel coils. So
Yes.
if one, yeah.
Yes. So there should be a parallel coil. So, and I was telling you, in real practice, really there is one more parallel, that because quenching occurs and then it does not get back to the normal operation, and by then you need to use the other one. That's why anytime it should be ready. It's always there is on additional, this means in parallel. And then again it might happen that continuously something happening, fault coming, going, etc. Some issue is going on in a particular portion of the network. That's why the good one will work, and then again that will go under quench, and it takes some time to get recovered to its normal mode. Then again by then the other will be fine, that got quenched before. In that way it might. That's why always there are two. So did you all write the same thing, that there can be one more parallel?
Yes, Dr. Ali.
Okay, fine. Now, how does a bridge type FCL, VFCL, differ from a DC resistive SFCL? So here, what did you write as answer? Do you have the answer with you? Those hard copy that you uploaded, I mean the PDF file. Does anybody have with you, or you don't have those things right now?
I do have it, Dr. Ali.
So what was the
Yeah, we
answer?
have it.
Yeah, what answer did you write for 2?
I know it has two different paths. One is the diode path and the other one is the shunt path.
That is for the BFCL.
Yes.
So the question is, what is the difference between bridge type and then DC resistive path? Oh, so that is the only answer you wrote. Yeah, okay, I see. Yeah, that is right. That BFCL has two paths. In addition to that, the bridge part, there is shunt path. In case of DC resistive, there is no shunt path. And what else? What is the additional difference? That is right. That is on point. And what else?
I think DCFCL, it needs cryogenics to maintain the superconducting mode.
Yeah, right. You see,
However,
yeah, right, exactly. You see, by the term, is still the SFCL. It is just, I mean, for the first term, it is normal SFCL. It is not DC resistive type or not other type. It is the conventional one. There is no DC system, fully AC based. And then, but it's still here, it is DC resistive, meaning that there is a DC path with the help of that diode system. There is rectification system, but it's still, it is superconducting fault current limiter. This means that Manoj said, like he's right, DC resistive SFCL requires the cryogenic system to maintain the superconductivity. It needs refrigeration system. But the BFCL, it does not require. This is not the superconducting. So therefore, the Amani, that point you mentioned, then as a second point, you have to mention that DC resistive still requires the superconductivity, but whereas BFCL does not need that superconductivity. And that's why there is the sound path. For example, we can see this figure, although it is for this problem, but you see this is that BFCL model. The sound path. So during normal conditions, sound path does not work. Current flow is through this one. So therefore, because during normal operation, this is not getting heated up, there is very leakage current in real practice, but that is no problem. So it gets cooled down automatically. So that's why you don't need refrigerator in this case. That is the difference. Okay, the next one, how does a bridge type FCL differ from a parallel resonance FCL? So again, this one is that VFCL versus the parallel resonance. So what answer did you write?
I wrote PRFCL has a parallel LC resonance circuit,
Yeah.
but other has like RL sound path to limit the fault current.
Yes, right. So therefore, currently this figure, this is the structure of that VFCL. What Manoj said, that's right. And if it is parallel resonance, then there will be parallel, and that is the capacitor. So this means in the shunt path, there is resistance inductance, and in parallel with the capacitor. And that capacitor and inductor form the resonance. And because they are placed in parallel, accordingly it is called parallel resonance fault current limiter. So that is the difference. So everybody, did you write the same thing?
Yes, Dr. Ali.
Yeah. That probably you might tell other point if you like, but at least there should be that basic difference. Okay, then moving forward, the following BFCL system can be used for transient stability improvement of a power network. Question 1. What are the function of diodes D1 and D4 and the DF? And question number 2. What is the function of the shunt path consisting of RSH and LSH? And question 3. Between RSH, this one, and then RDC, you see there is another resistance here, RDC. There is one L here, but there is another L here. And there are 4 diodes and DF, and this is the number 5 diode. So between RSH and RDC, which one is larger? So therefore, the first question, what are the functions of diode D1 to D4? This means, so what answer did you write?
It is for the DC rectification. I mean,
So
AC2.
yeah. So therefore, question was D1 to D4, meaning that D1, D2, D4, D3 for all 4 that is being asked. That's why it's a D1 to D4. So that's right for rectification. And then can you specifically tell about the role of, for example, D1 or D4 or D2 or D3, which because the AC is coming and that system is rectifying. That's right, 100% right.
Mm-hmm.
So then AC is coming. AC has positive peak and negative peak, right? AC signal.
Mm-hmm.
So which 2 diodes are working during positive peak and which 2 are working during negative peak?
So D1, D4 for the positive cycle,
Yes.
and D2, D3 for the negative cycle.
Right. So everybody, did you write the same thing?
Yes, Dr. Ali.
Okay.
Yes,
Dr. Ali.
Yes. Okay. So great. And then what is the function of DF? Or did you write?
So it's a free-wheeling diode to discharge the source current stored in DC limiting reactor while the switch is open.
Right. So here you see switch open, but actually the switch will be closed under steady state condition during normal operation. So this is the flow of current. Once there is fault, then this will be open. But because you see this is the DC path, so that inductor is storing the energy, half L I square, using that equation that you did several minutes back in the problem. So now you need to discharge that one. That's why, and you know, this was the direction. Switch got open, so there is no way to go. So now the freewheeling diode, it will make the free that energy. It will release the energy. It just take a little while, but it will At some point, it will be empty. So that is the function. And then what is the function of the shunt path consisting of RSH and LSH? What it is doing?
Limit the current flows.
Yes, right. So that is the main, actually, the current limiter. So it is limiting the current. And between RSH and RDC, which one is larger?
Of course, RSH should be larger.
Yes, right. So therefore, this one is really very, very negligible resistance, this one, in this path.
Excuse me, which one? Can you repeat, please, Dr. Ali? Which one?
Oh, so RSH is larger, this one. So you are comparing this RSH, which is in the shunt path, versus this RDC is here. So therefore, write down the RSH is larger, because that is your main fault current limiter.
Oh, yes, yes, Dr. Ali. I thought you said the opposite. I'm sorry. Yes, you're right.
Okay. Did you write that one?
Yes, I got it right. Thank you.
Okay. So therefore, Venkat, everybody is fine. Sindhuja, could
Yes,
you
sir.
follow me? Sindhuja?
Yes, Dr. Ali.
Okay. So you see your answers and then you can write down, and then once I will post the grade and then you can see that where you made mistake here. Okay. So then moving forward, the question number 5 was, in the following DC resistive SFCL system shown in figure 2, this is that DC resistive SFCL. The 4 diodes D1 to D4 are used, while a conventional SFCL as shown in 3 does not require any diodes. So this is that pretty conventional superconducting. It does not require diodes, but here there are diodes. However, both devices can be used for transient stability enhancement of a power network. Therefore, if you Google really, you will see the application of both systems well reported in the literature. So then what is the motivation to use a DC resistive FCL even if it increases some cost as compared to SFCL? So like before I was discussing that still it is SFCL, and of course this is SFCL. Both requires that cryogenic system superconductivity. So you cannot avoid that cost. And then when we are comparing, like it has 4 diodes. So that may increase sub cost. So that is the question. Then what is the motivation to explore this one? So what answer did you write?
I wrote like, because LSCBF is a short in case of DC, so which eliminates the Q loss and increase the efficiency in DC resistive SFCL, while conventional SFCL does not have such capability. That's what I wrote.
Yeah. So therefore, because you see this is, I mean, there is switch here, whatever. I mean, ultimately the AC current is coming. It is AC. So therefore, because it is based on the AC, during normal condition also the AC current is flowing. So during normal condition, there is some sort of loss, reactive power loss, because that is AC. And to avoid that loss, this system has been established. Because it is rectification, so therefore the DC current is flowing. So that's how, in order to avoid reactive power loss, that DC resistive SFCL has been explored. That is the motivation. That even though there are 4 diodes, and really those are not that much expensive. It is not like that those diodes will increase the cost 1,000 times. It is not. Maybe only a few $100s might increase. But still you can avoid losses and system efficiency will increase. Did you all write accordingly?
Yes, Dr. Ali.
Okay.
Yes, sir.
Okay. So then the next one, consider a double line to ground fault occurs at point F1. So this was that F1 in the following hybrid power network as shown in figure 4. And you placed a DC SFCL at the induction generator terminal to maintain transient stability. So this is induction generator, this is synchronous generator. So therefore, you put on SFCL here. Whatever the type is, in this case, it is DC SFCL. It could be this type or other bridge type, whatever you placed it here, and it maintain the transient stability, and it worked well. But then you noticed synchronous generator is facing the rotor angle stability because it is the connected system, integrated system. Because you connected here that fault current limiter, it worked. This generator looks fine. Like after installing, you are looking the profile everywhere. What is the voltage here? What is the power here? What is the speed? And again, you are looking the parameters here. Then you notice that synchronous generator is facing rotor angle stability. The kind of it is oscillating. So then how can you solve this issue? So what did you write? So meaning that synchronous generator is not properly stabilized because you used DC SFCL here. So because it was closest, so that helped this generator, but that did not properly help this generator. That is the meaning. So therefore, as a solution, what did you propose? What did you write here? Lakshmi, what did you write? Do you have that? Do you have the answer that you submitted?
Yes, Dr. Ali.
So what did you write here?
Due to low impedance path along the synchronous generator, the fault current was diverted, and caused the rotor angle stability issue. So I'll use the parallel resonance FCL to resolve this.
So that parallel resonance, where you like to place? I mean, instead of DCSFCL here, that one you mean? Oh, so
Yes, Dr. Ali, because in case of faults, when both a parallel FCL resonance is equal, it will limit the fault current magnitude and it will resolve the stability issue.
so therefore, the thing is that in this case, the example is DCSFCL. Then think about it is BFCL or whatever parallel resonance, you placed it. And then again, the same thing, it worked well, but still you are saying that issue is here. This generator is not fully stabilized. Even it might happen that you are using parallel resonance. Of course, parallel resonance parallel resonance PRFCL is much better than this structure. It is well proved, but still that can well maintain the stability of this generator. That may not maintain the stability of this generator. That is the issue we are facing. That was the question, that under that, how can you solve? This means
So I wrote, in this case, we need some auxiliary means for active power control, such as breaking resistors or PSS or energy storage for a synchronous generator. And the second option is we could use the global variable to choose the optimal point for the installation of FCL so that they are in synchrony, all the generators.
Yes. So Lakshmi, then you notice because this is facing and we did not put anything. Now you can, like Manoj said, that he is proposing breaking resistor or an energy storage. Now that thing you are telling that parallel resonance fault current limiter, you might choose to place that on here. Therefore, in addition to this one, therefore you put on solution here. So that is not enough for both system because it is far. So the thing that we are explaining, that what is the reason? The question was not what is the reason why it is not stable. Question was, you see, how can you solve the issue? So therefore, you can propose that I can put that PRBFCL here, for example, parallel in addition to that DC.
Yes, Dr. Ali, I also wrote this. I thought I also wrote the same for one here at the synchronous generator and this DC SFCL at the induction generator, so that it will limit the stability issue at the synchronous generator.
Oh, so did you write that you want to put that on here? I mean, at the terminal of the SG. Did you write that on? Still, I did not write your, as I said, I started looking, but I did not complete. So I'll be looking. So therefore, everybody see, here you need to put on solution. in addition to this one. Or same thing might happen. For example, you did not put anything here, you just put a solution here, whatever it is, parallel resonance or braking resistor or energy storage. But then that might work well for this system, but this system may not be stable. So there might be problem. So therefore, you can propose solution both here and here, or also Manoj mentioned one point, you can find a common point somewhere here along the line. It might happen that here or here at this point, because there is, you see, a little distance and there is impedance 0.05 plus j.3, the impedance of this one. So you can choose, okay, I will be placing here or I will be placing here. That might be a common or optimal solution. Then only one might be okay. So that unless you simulate and unless you try placing that one, you are not sure that that can be the optimal or which location. So therefore, at least then in this situation, in the context of this question, you should write that, okay, there should be another solution here because one is not enough. Okay, so did you all write? What did you write, everybody? Kamana, what did you write as an answer for this one?
I wrote same, Dr. Ali.
Oh,
For
okay.
synchronous generator,
Okay.
active power controller, and for induction generator, reactive power controller.
Okay. So therefore, no, here there is already solution. This is exception. There is one here. Therefore, if you want to put one more again in here in this, then that will be again too much here. Yeah. Over control it will be. You see that you applied the DCS at the induction generator terminal. So therefore, you must not over control either here or here, because already there is on, and of course you have to look about the cost as well. So therefore, we must not put two solutions to protect one generator. Therefore, there is already one. Expectation was that that may be okay for this one, but unfortunately, that did not stabilize. That thing we are discussing. So this means some cost will increase, but we have to put one here. Or the Manoj is telling that there can be strategy. We might need to find optimal solution. After placing that, then you can see that whether it is stabilizing both or not. Yeah. Okay, so then move forward. This one, okay. The following figure depicts a series dynamic braking resistor (SDBR) topology used to stabilize a power network under transient condition. What should be the status of the bypass switch during a fault in the network? Explain your answer. So this means that you see bypass switch is a switch. Just take about a switch. Whatever it is, conventional switch or GTO switch or IGBT based switch, it's a switch. It open and it close. And there is a controller. So should it be closed or it should be open under fault condition?
Should be open.
Right, yes. Because during normal condition, you see, it should be closed because it is the SDVR. So you see, this is the line current. AC current is coming. And if you keep it, you know that open during normal condition, when there is no fault, then current will flow through this path. So there will be always resistive loss. So that you don't want. So that's why during normal condition, switch will be closed, and then this will be the path to current flow. So that's why it is called the bypass switch. That it is bypassing. It is not allowing to go current, because in case of the ideal switch, resistance is 0 here. So full current will flow through this one. And once there is fault in the network, because you need to reduce the magnitude of current, you need to improve stability, so the switch will be open. So therefore, the answer is the switch should be, the status of the switch should be open during fault. Did you all write that thing?
Yes, Dr. Ali.
Okay. Then the last question for the quiz was, consider in the power network of figure 5. This was the figure 5. following a fault, you want to stabilize voltage at bus number 5 by using a controlled VFCL. So what signal will you use to design such a controller? So this means, you see, it is called IEEE 9 bus. There are 9 bus. This is bus number 5. So you noticed that once fault happened, that this bus is facing voltage stability issue, and you want to stabilize this bus with the help of a control VFCL. So therefore, what should be the control input for that VFCL? So what input did you write?
I wrote TKED because all other rotating machines, we don't have renewables or DC sources like PV and others.
Yes, so that is of course one answer, and also because in this case particularly, you need to stabilize the voltage. Of course, that TKED will stabilize the system, but because in this case specifically it is the voltage stability issue, so it would be better if you use that total voltage. Total.
Okay.
Yeah, but TKED can also help. Yeah, I mean, your answer is okay. Your answer is right here. Yeah, I mean TKED, but so if you use TKED versus the total voltage in this case, then if you look the performance, voltage stability will be little bit improved with the voltage versus the TKED.
Okay.
But TKED is also okay. But the appropriate will be, the exact will be using the total voltage. When it is the rotor angle, everybody see, when it is the rotor angle stability or the speed issue, then use that total kinetic energy information. And if it is specific, if you notice that voltage stability, it is better to, it is recommended to use the voltage signal. Yeah. But still, if you write TKED, then the answer is okay. Did you all write same thing or you write different thing? Lakshmi, what did you write as an answer for this one?
I also wrote TKED, Dr.
Oh, okay. Yeah. So therefore, everybody, I think you listened and you understood. Therefore, of course, that is okay. That is acceptable answer. Then, and that is logical. But as I said, it is preferred and recommended to use the voltage signal. Yeah. Therefore, really, if you simulate this system and you design a controller, and one time you make TKD and second time you use total voltage, you will be collecting voltage from here and here, from the two generator terminal, and use that signal, then you will notice that there is somewhat better result, improved result. Okay, so then now I will discuss about what is that one? Your midterm exam. That means okay. Can you see the midterm exam 2?
Yes, Dr. Ali.
Yes, sir.
Yeah. Okay, so the first, this is, you see, 8310 for the PhD students, and then later I am opening for the must 7310. I think there was one question. I think first question was different, probably. Yeah. So I'll be discussing the theoretical questions only. Yeah. You see, does any type of synchronous generator have AVR, automatic voltage regulator, and governor control system? Explain your answer. What is the question?
Dr. Ali, I wrote only non-salient pole synchronous generators will have AVR and governor regulator since their speed is very high.
Okay, just hold a moment. I think for the, just a moment. For the, can you see the other question that I am scrolling? Yeah. Okay. Yes, I think for the master's student, it is question number 7B. Can you see this one? question number 7B?
Yes,
Yes, sir.
Dr. Ali.
Yeah. So therefore, does any type of synchronous generator have AVR and governor control systems? Yes. So yes, I think the same question. Yeah. Although I said there is on difference in on question, but I think I asked that question here for the master's student. Okay. So I am coming that on later. Okay. So then what, Lakshmi, you are telling something? What answer did you write? Lakshmi or Kamana? Who was talking?
I'm Lakshmi, Dr. Ali.
Yeah. So you are talking, right? Yeah. So
Yeah.
yeah. So yes. What answer you wrote? Can you please?
Only non-salient pole synchronous generators will use AVR and governor B, since they are used for high-speed applications. Their shaft oscillations and the oscillations and vibrations will be more, so that we use only these controllers for non-salient type synchronous generators.
Okay. And what else? Anybody else? What you write?
So what I wrote is generally all the synchronous generator has AVR and governor, except for the PMSG used for the wind generator, because it has permanent field magnet, which does not have any field control for voltage, because it doesn't need, it doesn't draw reactive power from grid for magnetization of the field. Since there is no dispatchable energy source in case of wind generator, in that case, there is no need of governor. Instead, pitch controller is used. That's what I wrote.
Yeah. No, so what you said, that is okay. Even you don't need to mention about the wind generator, like PMSG used with wind generator. That is right. That is right.
Yeah.
But
I wrote that.
That is right. Now, what I'm saying, that even the PMSG used with conventional system, not with the wind generator. Even there are example. These days, like for example, these days as an engineer, if you choose that conventional synchronous generator versus the PMSG, like you should choose the PMSG. The reason is that if you use the PMSG, then you can avoid that AVR system, because it is the permanently magnetized. So you don't need any excitation, and consequently, because you see why I am saying that you don't need AVR. What is the function of the AVR? AVR controls the terminal. Okay. Amani, maybe your baby.
I'm sorry.
Okay. Yeah. Okay. So you can take care of him. Is it him or her? Yeah.
He's a boy.
The boy. Yeah, okay. You can take care. Amani, you can take him away, and then.
I'm sorry about that.
Yeah. You can. Yeah. Okay. So everybody, can you hear me? Yeah.
Yes, Dr. Ali.
Okay. So therefore, what is the function of the AVR? Because you know that AVR, it takes voltage as the input, and then it produces the field voltage. It controls the field excitation. Therefore, if it is permanent magnets in PMSG, then you don't need the AVR. So you have no option to control the excitation because it is permanently magnetized. So that's why if it is, so therefore you just simply say if it is PMSG based synchronous generator, then there is no AVR system. So therefore, Lakshmi, do you get it now?
Yes, Dr. Ali.
Yes. So therefore, Sindhuja, what did you write as an answer for this one? Or Kamana, what did you write as an answer for this one?
I read all synchronous generators have AVR and governor.
Oh, okay. I see. So therefore now you understand, right? That if it is PMSG, and then Manoj is specifically telling about wind generator. So the Manoj, that is right. I mean PMSG, but even PMSG without the wind generator, as I said, these days synchronous generator all are like PMSG based. So that
I just wrote as an example for the wind generator.
Yeah, no.
I wrote for PMSG.
Yeah. I mean for the wind, that is correct information. But what I'm saying that even though you don't need to give example of when conventional machine has also conventional system can have also the PMSG and
Yes,
you
yes.
can use the but that you mentioned that is fine. Okay. I think then from question number 2, you know that master's student also you have the same thing. Yeah. Therefore everybody look. Yeah. Amani, did you come back or still you're out? I think says probably says out. Yeah. Okay. If suddenly a large load is rejected from a power network, how will the system stability be affected? In such a case, can a thyristor switched breaking resistor or a capacitor help maintain the stability of the system? Explain your answer. So, if large load is rejected, meaning that taken out from the power network, will there be stability issue? Or did you?
Yes.
Yes.
Yes,
So,
Dr.
yes. So, under that situation, so which one you would use? Thyristor switch breaking resistor or the capacitor? Can they help maintain stability?
So we would use thyristor controlled breaking resistor.
Okay, yes, that is the right answer. Because in this case, you are taking out the power, so therefore generator will be accelerated. System speed will be higher. Now you need to suppress that voltage. You need to break down that voltage. So the thyristor switch breaking resistor is the appropriate answer. Okay, then a static synchronous compensator, STATCOM, is used to maintain the transient stability of a power network consisting of synchronous generators and induction generators. Is there any adverse effect of using the STATCOM in the power network? So what did you write as answer?
So
Do you have the answers with you, everybody, or
let me check. Yes, Dr. D. I wrote STATCOM is generally used for reactive power control. So the mentioned power network lacked the active power control measures since STATCOM could not control the active power. However, governor is there in synchronous generator for steady state speed control. So along with STATCOM, some breaking resistor or some other active power control means should be implemented for transient stability. That's what I wrote.
So in this case, the question was, is there any adverse effect, meaning that the negative effect? Like what you explained, those all are like beneficial thing, like STATCOM can, I mean, and clearly it is mentioned, it can maintain the transient stability and then breaking resistors, everything, all are like beneficial side. But question was, is there any adverse effect of using the STATCOM in the network? Negative side, yeah. So come on now, what did you write? Are the answers with you or those got lost or?
I also write the STATCOM only control the reactive power.
Okay. That you can say the limitation in terms of, but it is the adverse effect. So adverse effects, you know, it is the negative sense here.
Yeah, it was really confusing at that time. I mean, I was thinking,
Maybe quickly you read. So that is the capability or the limitation of the STATCOM that you are mentioning that it can control, but it is the adverse effect, means negative effect. It cannot control the active power. That is okay. That is not its adverse effect. That is its limitation in capability. But while you are switching to control the reactive power, because you are continuous switching, you know, these are the power electronic based control, right? The STATCOM has that step down transformer, then there is VSC, and then there is a small size of capacitor, which is DC link, and it is bidirectional. So there are those IGBT and then those diodes. So continuously they are getting on and off with the pulse signal. So therefore, when they are continuously on and off, meaning that they are controlling the active power, they're injecting, they're taking out, in that way control. So therefore, what is the adverse effect? So Lakshmi, what did you write? Yeah.
I
also don't know, Dr. Ali. I just wrote the advantages of that STATCOM, and I wrote that during fault conditions, the relay will the relay and circuit breaker may misoperate
Oh, okay.
under transient fault conditions.
Oh, okay. So then again, you went to up to that grid level, that side. Yeah, okay. So therefore, everybody see, I think I'm not sure this one or maybe during the braking register, I was discussing with you, because you are controlling that reactive power to stabilize the system. So then ultimately, that impact will go on the shaft system as well, because you are continuously making switch on and off that STATCOM with the help of power electronics, and consequently the impact will go until the shaft system. Therefore, there can be some soft shaft oscillation, and sometimes it has been seen in real practice. If it is too much, then there are example of shaft damage, or the shaft section got damaged. So therefore, adverse impact of using the STATCOM or braking register, it might happen depending on how much switching is happening. Impact might go on the shaft system. It might be too much oscillating. Like it was able to maintain the stability, that is fine. Your system did not go unstable, but the impact might go on the shaft system. Sometimes it is called shaft fatigue. So there are some examples with the even braking register. Too much, it is switching, that thyristor switch braking register, too much switching is happening, and impacted went up to that shaft system. Shaft system might be too oscillating, even might be damaged on of the shaft section. So that can be the adverse effect, in fact, of any type of controller. Now, how much is the too much? Sometimes like earthquake happens, and it does not mean that earthquake in any particular city or particular zone that all houses will be damaged. It is not, right? Yeah. Sometimes some houses got broken, sometimes no. A little earthquake. It depends on what is the intensity. But that is the negative side, drawbacks of the earthquake. Again, after a few days, if there is another shock, then maybe house might be damaged, because already that the grounding base of the house got little bit unstable, a little bit loose. That's why there are examples that those devices, in one hand they maintain stability, but the adverse impact goes until the shaft system. Okay, then moving forward, for transient stability improvement of a power network, how can you coordinate the operation of series dynamic braking resistor, automatic voltage regulator, governor, and circuit breakers located on the faulted line? So what did you write as the answer for this one? So is there any sequence, or all could be operating at the same time? So Manoj, what did you write as answer?
So what I wrote was the AVR and governor usually operate under steady-state conditions. So irrespective of any transient stability, this should operate continuously 24 hours a day.
Mm-hmm.
So for any transient stability improvement, first circuit breaker located near to the faulty line should operate, and it should open in order to isolate the faulty parts. And then STBR should operate to reduce the current. That's what I wrote.
Yeah, but in this case, you see, it is the SD series. Yeah. You see, it is the series braking resistor.
It should operate first.
I mean, simultaneously. Now, yes. So therefore, what you said, that is right. AVR and governor, they are equipped. So they are working always, right? Yeah, irrespective of the fault, they are working. Yeah. So those will work definitely. And again, the thing is that it depends on how much inherent delay in each system. So like circuit breaker, as I was discussing, it takes about 5 cycles, or fastest circuit breaker 1.5 cycle. So therefore there is some delay on the circuit breaker. But then again, series dynamic braking resistor, as I was showing the picture, there can be controller, might be some delay. And then automatic voltage governor has also some delay. But then in this case, you cannot make any specific sequence, because SDBR is connected in series. And once there is fault current will start flowing through the SDPR because that is connected in series. So, and then circuit breaker is again in series. So therefore, in that case, you can say that all will be kind of operating almost at the same time. It does depend on how much delay is inherent delay in each system. Now, if you compare circuit breaker versus SDPR, both are connected in series. It depends on the delay. If the controller needs more delay for SDPR, then that will come later. Or it might happen that before the circuit breaker that may be activated. The same thing, AVR governor, if their time delay is less than SDPR circuit breaker, then of course they will start working. So therefore, in this case, there is no particular sequence. Like all might work simultaneously. Okay, then I think we don't have much time. Let's quickly go over. Okay, while both a series dynamic braking resistor and a series capacitor work as series control devices to maintain the transient stability of power network, how do they differ? Which control device will provide higher impedance in the circuit? Now what we are telling that SDPR. So you understand that SDPR will control the magnitude of current and maintain the stability. And what does the capacitor will do? Series capacitor. Like you have a switched capacitor and then you want to connect it in series. Similar to the SDPR, there is a bypass switch and then during fault you connected the capacitor, but that series. So then how do they differ? What capacitor will do if you connect in series? Okay, therefore everybody see, the line have already R and L, right? Yeah. Every line, every transmission distribution line, any portion of the cable has some inductance and resistance, right? And then if you connect the capacitor in series, what is the function of the capacitor? It will try to compensate some of the inductive effect. If it is fully the same XL, and if your XL value and XC value is the same, that will fully compensate the inductive reactance. Fully they will be cancelled and power factor will be fully 1. I mean, in real practice that does not happen, but at least you can understand that in your circuit you have the R and then already there is L minus JXA. So what it will do? It will reduce the inductive effect. So that is the difference. So when you are connecting the series braking resistor, because this is a resistor simply, so therefore you are adding the resistance in the system. You are not, resistor cannot compensate the inductor, right? Inductor is inductor. So the line has already the resistance, plus you are adding another resistance, say SDPR. So therefore you are totally increasing the resistance, and that's how it reduces the voltage and the stability is maintained, reduces the fault current. On the other hand, in case of capacitor, it is not doing anything with the resistor, but it is cancelling or it is compensating the inductive effect. So consequently, then power factor is getting improved. So everybody, could you follow me? Do they make sense?
Yes, Dr.
Yes, so you think that you have a line, and in the line you are placing SDPR, and in other case you are placing the capacitor. So you draw the circuit and then see that how do they differ or not. Which control device will provide higher impedance? Therefore, when you are adding the SDPR, that is increasing the impedance, or when you are adding the capacitor, that is adding the impedance of the circuit, of the line. Which one?
So what I wrote is like it depends on the element value as well as frequency for the capacitor.
Yes, so I mean that is right. But think the first case SDPR. SDPR is increasing the impedance because your line has the line along which you are inserting the SDPR. Already there is R and there is L, JXL, plus R plus R. So therefore total impedance J is root over R square plus X square. So therefore impedance is increasing. What is capacitor doing? You are not, because you are not adding any resistor, rather than you are compensating inductor. So therefore impedance will be lower in case of the capacitor. So therefore the question is, which control device will provide higher impedance? The STBR will provide higher impedance. That is the answer. And then when I am telling you the explain, then you explain how it can.
It was very confusing at that time.
Yeah, because in the exam you are working, but think carefully.
Yeah, that completely makes sense.
Yes. No, that is the reason I am answering, because as I said, maybe hopefully by tomorrow I will post the grade, and then so that you can understand where I have got the grade. That's why beforehand I am telling you the answer, and you can correct so that it makes sense. Okay, then following a fault, a circuit breakers open and then reclose after a certain time. That you know. Why is reclosing done after some time interval, not immediately after fault clearing? So why that time is needed? Like circuit breakers open. And then we discussed that, we discussed circuit breaker open within 5 cycle. And then we said circuit breaker reclose like after 30 cycle to up to 60 cycle. Why reclosing is done after that time interval? Why that 30 or 60 cycle is needed, not immediately after fault clearing? Yes.
Because the arc can be extinguished instantly in the circuit breaker, so circuit breaker cannot reclose immediately.
Right. Because you have to wait until the arc gets extinguished. Everybody, could you follow me?
Yes,
Yes, sir.
clearly.
Yes, please you all note down the answers or you correct your thing and then we can see. Okay, so what is an infinite bus? What did you write?
I think you asked this question in the first exam as well.
Oh, really? Yeah. Okay. So what is the infinite bus? The voltage and the bus where the voltage and frequency is constant. Of course, within a certain limit.
Yes.
Okay, and then assume several three-phase synchronous generators are providing power to a grid point. Under what condition can you add a new generator at that grid point, maintaining stability of the network? So what are the conditions? Then you can add a new generator at that grid point so that there is no issue, stability issue.
So all the generators should be in synchrony and they have to have same frequency, voltage, and phase difference.
Yes, and also the same phase sequence.
Yes.
Did you all write the same thing?
Yes, Dr. Ali.
Okay. I think we are almost done. To augment the power system stability, sometimes series connected means and sometimes parallel connected means are used. Is there any major objective behind their usage? So series connected device means basically they will be controlling the current, and parallel connected device means they are voltage based. So they operate based on the voltage. And series connected device, because it is series connected, so the dominating factor will be controlling the current first and then the voltage. In case of parallel connected device, first thing is controlling the voltage and then the current. That is the objective. Therefore, both ways system stability is maintained. In one case, it is current dominated, and parallel connected device are voltage dominated. That is the thing. Okay, this one. What are the causes of time delays in an electric power grid system? I think you all were able to write down. We discussed that one. And what are the conventional times for opening, reclosing, and reopening the circuit breakers following a fault on the transmission or distribution lines? So therefore, conventional time for opening within 5 cycles of fault happening. Reclosing is within 30 to 60 cycles after opening the breaker. And then again reopening within 5 cycles. That reopening again, in case of permanent fault, that's why the reopening is being asked here. Did you all write the similar thing or same thing?
Yes, Dr.
Okay. Then this one, a control is desired in a power network based on the reactance of transformer connected to the network. Consider the transformers get saturated. Under such condition, which of the following controllers will you choose for the system? Is it PI controller or fuzzy logic controller or P controller or the PID controller. So therefore, here is the thing, because whatever it is, the transformer case or generator case or other device, because transformer gets saturated, saturated means your characteristics is non-linear. If it is unsaturated, then it follows the linear characteristics. Because it got unsaturated, meaning that it get non-linear. There is non-linear relationship. Even though the flux is increasing, voltage is not increasing. That is the meaning, not proportional relationship. So what answer did you write here, everybody?
So what I wrote is, under the saturation, the reactance varies non-linearly, so we cannot use any linear controller like PI or PID. So it is preferred to use some non-linear controller like fuzzy logic controller.
Okay, okay. Then everybody, did you write the same thing or you choose different controller? Lakshmi, what did you write?
I wrote a fuzzy I will use a fuzzy logic controller.
Oh, okay, okay. And what is the reason? You said that?
It does not operate only on reactance and will follow only the logic and improve the stability.
Oh, okay, okay.
All other controllers need reactive profile. So
Okay, okay. So the main thing is that fuzzy logic is a like non-linear controller. That like if then means if this is then this. That is kind of uncertain and non-linear situation. Yeah. So that's a fuzzy logic controller works well when there is non-linearity, imprecise, inexact situation. In this case, because transformer got saturated, so it is representing the non-linearity. So that is the reason you will be choosing this thing. Now, some of you might choose this on, or this on. Linear controller might work somewhat, but it will not work well like the fuzzy logic controller. So the fuzzy logic controller will be the appropriate answer. On the other hand, if it says the unsaturated, then you might choose any of these, PI or P or PID. It depends on the system, on situation. Then again, among these three, P, PI, and PID, in some cases, P might work better, some cases PID might work, some cases PI might work. It depends on the system. But you will be choosing those linear controller when it is like unsaturated case or linear situation. For non-linear situation, because I am specifically saying fuzzy here, therefore you will be choosing fuzzy. Or in other case, it can be any non-linear controller. Okay, so then do you have any questions or comments?
no, Dr. Ali, thank you.
Okay, so I mean, soon, I think hopefully by tomorrow you can see your grade, this one and that quiz. First I will be completing and then I will notify you. And then only then you can see on the Dropbox. Okay, so with that, thanks everybody for joining and see you on next week.
See you, Dr. Ali. Thank you.
Okay, okay, thanks.
Thank you.